Hi everyone. Welcome to the live stream this evening, and what I'm going to go over is the fluid dynamics stuff. I already did in last week's live stream. I already did some fluid static problems, but in fluids we have both fluid statics and fluid dynamics, and so this evening I'm going to do three fluid dynamics problems. And we just started on waves, so there's a lot of questions I can ask about waves, but I'm only going to do a couple of problems on waves, okay? And we'll do all waves next week at this time. All right, so let's start off with fluid dynamics. Dynamics means moving, and so these are problems or situations where some fluid is actually moving, okay? And there's two basic phenomena, or two conservation laws, actually. One of them is the continuity equation, which is based on conservation of matter, okay? Like fluid can't just appear or disappear out of nowhere. And so if you inject fluid into a pipe in one end, then the fluid's got to come out at the other end, okay? And the same amount that you inject in one end, the same amount has to come out at the other end. And so that creates a kind of a relationship between velocities and cross-sectional areas, okay? That's known as the continuity equation. The second one is Bernoulli's equation, and Bernoulli's equation is based on energy, okay? And energy, just like energy with particles or with like masses, there's a kinetic energy, 1/2 mv squared. There's a potential energy, usually due to gravity, okay? There's no springs when it comes to fluids, so there's like mgh, but we don't use m when it comes to fluids, we use rho. So it's not so much kinetic energy, but kinetic energy density and potential energy density. So there's 1/2 rho v squared and 1/2 rho v squared and rho gh, okay? But actually pressure itself is like an energy density, okay? And so if you take all three of those and you add them together, P plus 1/2 rho v squared plus rho gh, that quantity, that energy density, is the same all the way through a fluid, okay, when it's flowing, under the assumption of laminar flow, okay? So those are the problems that we'll do with fluid dynamics. Okay, so let's start. This first problem is a continuity equation problem. So a pipe has a rectangular cross-sectional area. Okay, so pipes are usually round, but just to make a variation, I'm going to make this pipe actually rectangular, and one end has the dimensions of 3 by 5 by 4. 3.5 by 4.5 centimeters, and another end has 3 centimeters by 5 centimeters, okay? And the one end, the 3 by 5, 3 by 5.5, and there's a fluid that's flowing in that end, and it's flowing in at 5 meters per second, okay? And I want to know how fast does it flow out the other end, okay? The verbal description here is sufficient, but let me just draw a quick picture of what this pipe looks like. So over here, we have like a rectangular going in here like that, and this is a pipe, so it's like it's like that, okay? And it actually narrows a little bit, and it goes to this, something like that. Sorry, it's not the best drawing, okay? So I guess I could put dashed lines for the back side here like that. There you go, okay? And I guess I could draw this in there like that, okay? It's kind of hard to draw a 3D rectangular pipe, but there's a fluid that's flowing in this way, okay? And of course, if the fluid flows in here like that with some velocity, it has to flow out like that with some velocity, okay? So we could call this A1. That's that cross-sectional area here, okay? So like this, that cross-sectional area there, that's A1. And the fluid flowing in there is V1. And then over here, this is a cross-sectional area A2. And the velocity of the fluid flowing out there is V2. And the continuity equation states that A1 times V1 is equal to A2 times V2. All right, so there we go. Let's let's actually solve it. All right, so over here, actually let me scroll up a bit. I know my image is covering the English there, but I'll just read it out for you. Okay, so we have A1 times V1 is equal to A2 times V2, like that. There's the continuity equation. And one end has area A1 equal to 3.5 centimeters by 4.5 centimeters. Okay, now you could convert this into MKS units, but you actually don't have to here because all of the information is in centimeters. Okay, so we can actually work with all of our areas in centimeters squared, and if you do, this A1 will be in centimeters squared, the A2 will be in centimeters squared, and then the centimeters squared will cancel out, and so the units will just work out. Okay, so in situations where you don't have any, like you have like an area on one side, an area on the other side, or velocity on one side, a velocity on the other side, as long as the units are the same on both sides, you can get away with not converting to MKS. Okay, but if you're in doubt, convert to MKS. You can't go wrong. All right, so let me calculate what 3.5 times 4.5 is equal to, and that turns out to be 15.75, and that'll be centimeters squared. Okay, so there's A1. All right, and the velocity there, no, sorry, the velocity there, V1, we don't know that one. That's the one we want. Okay, because we know that the water is flowing in the 3/5, which is going to be A2. We know that that velocity is going to be 5 meters per second, but the A1 we don't know. Okay, so A2, that's the other opening, and it's going to be 3 by 5.5 centimeters, like that. Okay, and let's see what that works out to. 3 times 5.5, it's going to be 16.5, like that, centimeters squared. Okay, and that velocity we know because the 3 by 5.5, the 3 by 5.5 end, that has a velocity of 5 meters per second. Okay, and so V2 here is 5 meters per second. Okay, great. So it really is that simple. So let's take this equation again, and let's just substitute in now. For A1, we have that number. Okay, for V1, we don't know. For A2, we have this number, and for V2, we have this number. Okay, 5 meters. All right, and I kept the units in there just to show you what's going to happen with the units. So you might say, are you sure that the centimeters will cancel out? Yeah, because notice on the left hand side here you have centimeters squared, on the right hand side you have centimeters squared, so those will cancel out. Okay, and of course then your answer is going to come out in meters per second. All right, okay, so divide both sides by 15.75, so V1 is going to equal this divided by this. Okay, and that will equal, let me get it on my calculator, it's going to equal this number there. There's more decimals, but I'm rounding off, and we should round off to 3 significant figures, so that 3/8 there just rounds off to 4, like that. Okay, there's our first problem. Okay, a continuity equation. Let me see if there's any questions in the chat. No questions. It is that straightforward. The only other thing I'm going to say to you is, what if I'd given you a round pipe? Okay, so if it's circular, well then you don't want to use length times width, which is what you would do with a rectangle. But if it's circular, you have to use the formula A is equal to, and let me get a symbol pi here. Pi r squared. Okay, and this is for a circular cross-sectional area. All right. But you've probably seen that a lot of times. Okay. Again, just to be a little different, I decided to use a rectangular cross sectional area. All right. So let's move on. Okay. So the next question is actually a Bernoulli's equation. Okay. Problem. And let me read it and we can go through it. So a wing under water, okay? So like you know how airplane wings they're shaped. I'll draw it in a minute, but the upper part has more of a bulge than the lower part. That forces the air to flow faster across the top than it does along the bottom, okay? And so that's what we have here. It's the wing, but I put it underwater because water has a bigger density, okay? And so the effect will be the pressure difference will be a lot bigger, okay? That's the only reason I did that. And you can have wings underwater. I mean, submarines do have the little wings that they can use to deflect water, and that's how they can navigate. But whatever. So okay, so we have a wing underwater, and it's of negligible thickness, and you'll see why in a second. Okay, the water flows over the top at a velocity of 10 meters per second, and along the bottom at 7 meters per second. Okay, so the water has to flow faster along the top because there's more distance to travel. Okay, what is the pressure difference between the top and the bottom? And you go, wow, that how do you get that? I mean, there's just a difference in velocities, and from that difference in velocities, there's a difference in pressure. Yeah, that's Bernoulli's. Okay, so I guess you can tell the difference. Like a continuity question is when you're constraining the fluid to flow through like different cross-sectional areas. Okay, that's when you want to use the continuity equation. But the Bernoulli's equation is whenever you're trying to relate pressure, velocity, and height. Okay, and you'll notice that I said negligible thickness there. That basically says don't worry about the height in this problem. Okay, so let me draw a picture of what's going on here, and then we can do the problem. Okay, let me switch to this and create a new whiteboard. All right, so we have a wing, and what does a wing look like? Well, there's the bottom of the wing, and there's the top of the wing, like that. Okay, and when water flows along the bottom here like that, it can go more or less straight across like that. But when water flows along the top, it has to travel a longer distance because it's traveling along the top there like that, and it meets up so that, like, if you've got if you put a little red dot there and a red dot there, and you just follow the flow of the red dot, the two red dots, they'll match up at the other end. Okay, and you need that in order to not have turbulence. That's like the criterion of laminar flow. Laminar just means smooth. Okay, and as a result of having to travel a further distance over the same amount of time, the velocity up here turns out to be 10 meters per second, and the velocity down here turns out to be 7 meters per second, like that. Okay. Now, what does Bernoulli say? So I'll write this. We'll solve it on the other on my text editor. But basically, Bernoulli says if you calculate P, or if you get P plus 1/2 rho, that's the density of the fluid, V squared plus rho GH, like that, that quantity is the same at every single point in this flow. Okay, now I only drew like two little blue lines there, but like there might be more fluid flowing here, and then there's like fluid flowing like that. Okay, and you could pick any point you like. Okay, like this point right there, or that point right there, or that point right there, whatever points you pick. If you calculate this quantity right here, it gives you the same number. Okay, so it's the same value everywhere in that fluid. And by the way, that the units of this are joules per meter cubed. Okay, I won't prove that right now, but I did in the lecture. Okay, it's joules per meter cubed, and so it's joules are energy, and whenever you divide by like a volume, you get a density. Only it's not a mass density like rho. It's actually an energy density. Okay, so now where do you want to I just said you can calculate it anywhere and you get the same number. But to solve this problem, where do you want to calculate it? Well, you want to calculate it at the top of the wing here like this, where the velocity is 10 meters per second. And you want to calculate it at the bottom of the wing there like that, where the velocity is 7 meters per second. And so you have different V's on the top and bottom, okay? And as a result, you have to have different pressures. What about this term here? What about the rho GH? Well, that H there, like if you chose H equals 0 at the bottom of the wing like that, so that would be like, for this point right there, then the H for the other one would be up here. Okay, so this is like H equals 0 and this would be H. But I said that number is very small. Okay, it's very much less than 1. Okay, and so basically that height there is negligible. So whenever in a problem you hear me say something like, height is negligible or whatever, it just means you can ignore that term. Okay, so yeah, technically speaking, that's there. And if I told you the thickness, you should use that. Okay, but the difference in the heights is not going to contribute to anything. So we could just, drop that term. Okay, so let's go ahead and solve it. All right. Switch back to this screen. Okay, so what are we calculating? At the top and the bottom, we got to calculate this quantity here. P plus 1/2 rho, and let me grab a rho from here like that. Rho V squared plus rho GH. Okay, and we want to calculate that at the top and bottom. So let's do it at the top first. Okay, so over here, let's just say here top. Okay, and what's that going to equal? Well, the first thing you'll say is, what does P equal? We don't know. So how about we just say P and underscore top like that? Okay, so that's just the pressure at the top. We do know that it has to be different at the top and the bottom because I mean that's what I'm asking for. What's the pressure difference between the top and the bottom? We just scroll down here so you can see that. So the question was, what is the pressure difference between the top and the bottom? So we know there has to be, just from the question, but also because the velocities are different. And if the velocities are different, if these are different from the top and the bottom, okay, the kinetic energy density is different, and this one doesn't contribute, then the pressure has to compensate so that they're equal. Okay, so there's a pressure on the top, but we don't know its value, plus 1/2. What's the density of water? You should have this one memorized. In MKS units, it's 1,000 kilograms per meter cubed. Okay, I'll drop the units in a second because we don't need them, but just to remind you, the density of water is kilograms per meter cubed. Now, our tests are open books, so you could always look that up at the time, but it's a number you should probably have memorized. Okay, any other densities I'm going to give you, like I don't expect you to know the density of ethanol or to have to look it up on a test. It'll be right in the test paper. Okay, so there's that. And then what's the velocity at the top? 10. Okay, and that's got to be 10 squared. Okay, so there we go. There's our 1/2 rho V squared. Okay, and then plus the rho GH, but guess what? We're just going to drop it. And you might say, well, why do you drop it? Because negligible difference in height, whatever rho GH is equal to, it's the same for both top and bottom, and it'll just cancel out when we set the two equal to one another. Okay, well, all right, so now we've got that. Let me simplify that a little bit. So that's going to be this, and whoops. Let me do this, but let me actually remove the units. I guess I should put here meters per second just to show you that that's where the units are. Okay, meters per second, but I'm going to drop the units here, and so I can cut and paste into my calculator, and that should just give me this answer right here. Is equal to P top plus that. Okay, and lots of zeros there, but you know what, let me put in some commas just so we can see. So it's like 50 million. Okay, and the units of that would be, if we worked it through, they would be pascals per meter cubed. Okay, sorry, no, joules per meter cubed, or pascals. Okay, all right. Now what? Let's do bottom like this. So what does that look like? Well, it looks the same. Okay. And that's going to equal the exact same expression, except that now it's not 10 meters per second, but 7 meters per second. Okay. And that's going to equal, uh, let me, oh, sorry, I put top there. This should be bottom, right? Bottom. Okay, so um, this whole expression again, but I'm going to get rid of the units like this. And that's going to equal this. I have a nice calculator where if I just copy and paste what I see there, it'll automatically calculate it for me. So there we go. That's that. Okay. So now what? Well, we have that quantity on the top. We have the quantity on the bottom, and what? Bernoulli says that they have to be equal. So Bernoulli's principle says that this must equal this. Okay. And just to put some commas in there so you could see it, there's 3 and there's an, so this one's 50 million and this one's 24 million pascals. Okay. So so now what? Well, we take this and let me cut and paste it again. So what I'm going to do is I'm going to subtract the 24 million from both sides. Okay, and then that disappears. Okay, and I'm going to subtract P top from both sides. So then that disappears. Whoops, there we go, like that. Okay, and let's see what that's equal to. Okay, and let's convert that to, this is, what are the units here? Well, it's pressure in MKS units, which is pascals. Okay, and so this is going to be, well, there's 3, there's another 3, so that's kilo, that's mega, so this is going to be 25.5 megapascals difference between the pressure in the top and the bottom. Okay, all right, so there is 25.5 megapascals more pressure on the bottom than the top. Okay, notice there's more pressure on the bottom than the top. Okay, and what does that mean? So let's go back to the picture here. I know it's getting a little bit messy, but let me just show you. The pressure on the bottom is bigger than the pressure on top. Okay, and what does that mean? So there is pressure on top and there is pressure on the bottom, but the pressure on the bottom is bigger. That means there's an overall upwards pressure. That's one of the things that contributes to giving lift to a wing. Okay, so wings, you know, they lift airplanes. One thing, there's other things going on with a wing, so it's not just Bernoulli, but at least one of the things that contributes to the lift that a wing has is the Bernoulli principle. All right, so there's our first problem in Bernoulli, and it's rather different than the problem that I did in the pre-recorded lecture, because in the pre-recorded lecture what I had was, well, let me draw it for you just to remind you. What I had there was a beaker like this, and I had a fluid in there like this, and I poked a hole in here like this, and the fluid flowed out like that, and the fluid here had no velocity, and the fluid here, of course, did have a velocity because it's flowing out. Okay, so some positive velocity there like that. Oh, It's terrible. Some positive velocity like that, okay? And it did have a height. And so basically, and the pressure was the same at the top and the bottom, okay? It was like 1 atmosphere here, 1 atmosphere here, okay? And 1 atmosphere there. So that, the P part canceled out. But basically what was happening is the height gave a rho GH value, and that converted into a 1/2 rho V squared. Okay, in other words, the gravitational potential energy became uh, kinetic energy. Okay, so there's that another example of Bernoulli's principle. Very different than a wing, but still Bernoulli's principle. Okay, so oh, what did I do there? I don't think I showed you the picture, did I? Yeah, hold on here. Let me just show you the picture. There you go. So I apologize if you didn't see that. Let me just go over it again. So there was a beaker. Let me see. Can you see that? Yeah. The dangers of live streaming. Okay, so there's a beaker. This was the one in the lecture. There was fluid in the beaker. There was no velocity at the top there. There was velocity in the stream at the bottom there. There was a height, okay, and the pressure on the top and the pressure on the bottom were the same. So the pressure there, the P part, was the part that was the same and fell, dropped out. But there was a rho GH on one side, which got equated to a 1/2 rho V squared on the other side. So it was basically your potential energy becoming kinetic energy. Okay, let me see there is a question here. Why did you square the 1000? I don't think I did square the 1000. I hope I didn't. Let me take a look if I did. Oh, maybe I did. Did I make a mistake? Oh dear, oh dear. Yes, I did. Well, in answer to the question, why did I square the 1000? Let me answer. That was a mistake. Okay, so you know what? It's not that big a deal to fix. Yeah, I see what I did there. I have no idea why I wrote that here. So right there, get rid of that square there. Okay, and over here, get rid of that square. And of course, because I copied and pasted, I made the same error twice. And so let's take that and recalculate it. I thought the numbers were a bit large. Okay, so that's 50,000, sorry, okay? And of course here, if I don't square that, then that's going to be 24,000. And then over here, let's take out 3 zeros there, and 3 zeros there, and take out 3 zeros there, and take out 3 zeros there, and take out 3 zeros there. And so now it's not megapascals, but kilopascals. This makes more sense because megapascal is pretty big, okay? All right, so thank you very much for noticing that. I have no idea. Yeah, I have no idea why I wrote that square there. That's where it came from. It should have been. Oh, I know what I did. Yeah, this was like layers of mistakes. That's your density unit, kilograms per meters cubed, okay? And then when I went to take the unit out, first of all, I put square, which was one mistake, but then when I went to take out the units, I took out that much and I didn't take out the cube part, okay? And so I wound up with a square in there. That was like a typo, okay? So yeah, you want to square, or maybe I should move the square outside here. Okay. You want to square the velocity like that. See the velocity there? You want to square the velocity there, not the density. Okay? So, and then same thing up here. Yeah, see, that's one of the mistakes I made. And then let's move that square on the outside there like that. Okay? So again, that cube there is part of the unit. All right. Okay. So, so let me just say problem fixed or error fixed. Error fixed. Okay. Thank you for pointing that out. I purposely don't solve these things beforehand because it's not that I want them to be rough around the edges, but I want you to see how I reason them through, as I do them. Okay. So there's question number 2. Let's move on to question number 3. Uh, another fluid dynamics is also Bernoulli. Okay, so I have a syringe. Okay, and I think I did the syringe, a syringe that was horizontal in the lecture. Okay, but here I'm going to do a syringe, but I'm going to point it straight up. Okay, and of course I'm going to apply some pressure on the plunger, 100 pascals. That might be a lot, but I don't know. We'll see what number we get. Okay, uh, apply a pressure on the plunger, but because this thing is pointing straight up, the syringe is pointing straight up, the stream is going to go up, and it's going to reach a maximum height before it starts to come back down. Okay, so how high does the ethanol squirt? And the syringe is filled with ethanol, just because I don't want to use water for everything. Okay, so what does this picture look like? You don't really need the picture, but it's not bad to draw one. It helps. Okay, and so we have a syringe down here like this. All right, and here's the needle like that. Okay, and here's the plunger like that. All right, so there's a plunger. I hope that, what does that look like? Okay, not the best drawing, but there you go. And it's filled with ethanol here like this. So the blue there is ethanol. Okay, and of course, what it's going to do is it's going to squirt, and it's going to go to a maximum height, and then the stream is going to come back down like that. Okay, so that blue line is supposed to be my my ethanol going up. Okay, and now you say, okay, well, how do you do this? Well, remember, Bernoulli is always this. It's P plus 1/2 rho V squared plus rho GH, like this. Okay, and you want to calculate it at 2 points. And so the 2 points that you want to calculate it at, I guess that's part of the difficulty here, is like, where do you want to calculate it? Well, clearly one place you want to calculate it is up there. Okay, because you want to know the maximum height. Okay, and we can take the height of h equals 0 right here where the plunger is. So where that plunger is, that's h equals 0, like that. And right here at the top, h is equal to question mark. That's what we're solving for. Okay, so because we want to calculate h at the top there like that, we definitely want to apply Bernoulli to the top. Okay, but where else do we want to apply Bernoulli? I guess right at the plunger, because at the plunger, you know that I'm applying a pressure of 100 pascals. Okay, so great. What are the numbers that we're going to use? Well, first, let me remind you what gauge pressure means. Okay, so you've heard me use that term in the lecture. You go, what do you mean by gauge pressure? It really means how much pressure compared to 1 atmosphere. Okay, so when I say 100 pascals, I don't mean 100 pascals absolute. I mean 100 pascals in addition to hard to write here, in addition to 1 atmosphere. Okay, so it's like the 1 atmosphere is the background, but we ignore that. We just ignore that, and we just say how much in addition to that 1 atmosphere. 100, that we call gauge pressure. Okay, so the gauge pressure down here at the plunger, I told you, was 100 pascals. Okay, the gauge pressure up here at the top, that's 0. Okay, 0 pascals. Again, it's not that there's no atmosphere, it's that it's 0 pascals above atmospheric pressure. In other words, it is at atmospheric pressure, because when we're talking gauge, we're always talking in addition to 1 atmosphere. So it's 1 atmosphere up here. So how much more than 1 atmosphere? Well, 0 pascals more than 1 atmosphere. So when we go to use this, when we apply Bernoulli's down here, we're going to use P is equal to 100. When we apply Bernoulli's up here, we're going to use 0. Okay? All right, good. Now, what about the rho? What about the V? The velocity there. Well, what's the velocity at the top there? Okay, the velocity at the top is 0. Okay, remember when we threw like a ball up into the air? This is like when we were doing 1D kinematics way back at the beginning of last semester. And when the ball gets to its maximum height, what's its velocity? 0. This is the exact same problem, but in fluid dynamics rather than like a ball or some object. Okay, so the velocity at the very top there is 0. Okay, so this term will go away at the top. What about down here? How fast is that plunger moving? Well, the plunger's not moving that fast. Okay, remember, it's a very thin needle there, so the plunger's not moving that fast. In fact, if it's a big enough syringe, you might as well say that it's of negligible, the velocity is of negligible speed there. And so you could say V is equal to 0 there, like that. Okay, imagine the needle here is really, really thin. This needle right in there is a really thin needle. So that stream, that blue stream that you're seeing there, is very thin. And so, you're pushing on the plunger, and yeah, you're applying 100 pascals, but very little fluid is actually flowing out. And so the plunger barely moves at all. You might as well just say that the velocity is 0. Okay? Down there. So the velocity is 0 on the top and the velocity is 0 on the bottom. In both places, both top and bottom, we don't have to worry about the kinetic energy part. Okay? So what part do we have to worry about? Well, just this, the rho GH. H down here is 0 because we chose it to be 0 there. And H at the top, that's the unknown. And so basically we'll be able to solve for H. Okay? So what's happening in this problem, see, you've got 3 terms: pressure, kinetic energy density, and potential energy density. Okay, and they can, just like energy last semester, energies can switch between the total energy is conserved, but the energies can switch between them. Okay, they can slosh between the different types. In this one, you've got pressure down here, 100 pascals of pressure turning into height. It's like the pressure, the energy density goes from P into rho GH. Okay, that's kind of what's happening there. All right, so that's enough with the picture. Let me see if there's any questions before I switch. Looking good. Okay, so let me switch over to the other screen there, like that. Great. So let's go ahead and do it. Okay, so at the plunger, okay, we're going to be calculating P plus, let me just grab the symbols from up here. Okay, and the pressure at the plunge, so what's this going to equal? Okay, let me move that over a bit. The pressure at the plunger is 100 pascals. Okay, the velocity at the plunger, remember, it's negligibly slow, so that's 0. So V is 0, so that term is 0. Plus the height at the plunger, that was H equals 0, and so that's 0 there, like that. And so the energy density at the plunger is 100 pascals, like that. Okay, so that was easy. All right, what about at the top of stream? Well, same formula, but now at the top of the stream we're back to 0 pascals because we're back to atmospheric pressure. The velocity is 0 up there, but there is an H. Okay, so this term is not 0 this time. So rho, what do we use for rho? Well, I told you that the density of ethanol is 0.789 grams per cubic centimeter. That's not MKS, okay? MKS is kilograms per meter cubed. So what you want to do is convert. And you go, well, how do you convert from grams per cubic centimeter to kilograms per cubic meter? And let me just do a little bit of an aside down here. Remember what the density of water is? You can either think of it as 1,000 kilograms per meter cubed, or you could think of it as 1 gram per cubic centimeter. So to convert from a gram per cubic centimeter to a kilogram per cubic meter, you multiply by 1,000. Okay, so the density here for ethanol, there it is in grams per cubic centimeter. Multiply it by 1,000 and you get it in grams per cubic meter. Okay, that's another reason why you should have that number memorized, because it's also the conversion between two very popular units for density: kilograms per meter cubed and grams per cubic centimeter. In chemistry and biology and in the health sciences, people tend to use grams per cubic centimeter. But you know, for our formulas, you have to convert to MKS. So you'll want to know this conversion. Okay, so back over here for the density, we're going to use 789. Okay. For G, um, I'll tell you whether to use 10 or 9.8 on the test. Let's use 9.8 just to be a little bit more accurate. Okay. And then H, like that. Okay. And what's this work out to? Well, it just works out to whatever those two multiplied together are. Multiplied by H, like that. Okay. And so that's as far as you can go with this one. Okay, you can get down to there. And now what? What does Bernoulli say? Bernoulli oh, says that this must equal this. Okay, and so H, I guess 100 pascals isn't that much. H is going to be 100 divided by that number there. Okay, and what's that equal to? And there we go to three significant figures. What are the units? MKS units for height, meters. Okay, or if we want to convert that to centimeters, 1.29 centimeters. Okay, so in fact, this is not. For some reason, I thought 100 pascals was a lot for that, for a plunger, but it really isn't. Okay, and so the fluid would only really squirt up 1.29 centimeters. Okay, so well, there you go. Okay. Probably on a test, I would have made it more. I probably this is correct. Okay. So let me ask if there's any questions. I'll give you some more realistic numbers in just a second. So a more realistic number might have been something like maybe 10,000 pascals here, like that. In which case this would have been 10,000. That would have been 10,000. And then this would have moved the decimal over 2 like that. And then it would have been 1.29 meters. Okay, so that's like 10 kilopascals. Okay, now how does that compare? Like you might say, well, how big is 10 kilopascals? Like how am I supposed to picture it? So remember what one atmosphere is? One atmosphere is 101.3 kilopascals, like that. And so this is roughly a tenth of an atmosphere. Okay, so that's a bit on the high end. Okay, so what I gave you first, 100 pascals, was a bit on the low end. This one's a little bit on the high end, but still, you know, within something that you could do in the lab very easily. All right, let me see if there's any questions. Okay, so far we're done with the fluid dynamics. Okay, and let's move on. So you know, not to overwhelm you this week with too many videos to watch, I said just watch half of the wave equation, and so we'll just do a couple of wave problems right now, a couple of easy wave problems. Next week we'll do all of the wave problems, okay? Because by that point you will have been able to watch all of the lectures on waves. Okay, there's quite a bit on waves. Okay, so before I jump into the problems, so let me just remind you what a wave is. So a wave, let me switch to the whiteboard here. A wave is basically a collective phenomenon of oscillators. So you know, you say, well, what does that even mean? Well, I mean, imagine, well, let me do it in black here. Imagine a string here like this, okay? And imagine that the string is made up of like one mass here, and then there's another mass there, and then there's another mass there, and then there's another mass there like that, and another mass there like that. Okay? And right now they're just sitting there. Okay? But what if I grab one and I pull it up? I pull it up like that. Okay? So it starts to move up. Well, as it starts to move up, it starts to influence its neighbor to move up, which then influences its neighbor to move up, which influences its neighbor to move up. Okay? Now, that's the start, okay? Now imagine that after a while, I start to pull this down. Let's do that in purple. So I pull this one down, then it starts to influence this one to come down, and influences this one to come down, influences that one to come down. But remember, this was being pulled up. So this one's been going up, that one's been going up, that one's been going up, this one's been going up. So actually, this one is kind of up a bit, and that one's been up a bit like that. And then you say, okay, well, let me just draw kind of like an envelope on these. So let's do that in green. Okay, and your envelope would look like this. And I didn't draw it all, but there it is. You know, there's a part of a wave. So the green part is the wave part. Okay, and okay, let me make another whiteboard here. So here is the wave. Okay, remember it's made up of those oscillators, and those oscillators, they're moving up and down like that. Okay, but we're not worried about any one oscillator. We're worried about the collection of oscillators, and the collection of oscillators are forming that kind of a wave shape there, the thing in green. Okay, and you can say a few things about that. You could say, well, how far is it from crest to crest? And that is called lambda. And you could say how long, because this whole thing is moving. Okay, so it's moving this way. So you could say how fast is it moving? And you can also say how long does it take before this crest makes it over to that crest? Well, that time is called the period, but the reciprocal of the period is going to be the frequency. And the frequency is how many of these crests go by a particular point per second. So imagine that you're observing, I don't know, let's do it in red here. Like you're an observer and you're watching right over here. So you just keep looking down at that one point there like that. And you say, how many crests go by? Well, you know, like you're just seeing the crest there frozen in time. But this crest is eventually going to move over to here. Then it's going to move over there. Come over there. So then one crest goes by, then two, then three, then four. Then how many go by per second? That's your frequency. Okay, and that's related to the time it takes for a crest to travel from one point, one crest to its neighboring crest. Okay, the time that propagation takes, that's the period. Okay, and the frequency, of course, is 1 over the period. All right, so there's the theory for our first problem. Sorry, I was about to sneeze. I didn't though. Okay, so let's take a look at this one. Microwaves in a microwave oven have a wavelength of about 5 centimeters. That's actually correct. Roughly speaking, they're about 5 centimeters. What's the corresponding frequency? Okay, and you go, wait, whoa, isn't there something missing there? Yeah, there is. The speed of microwaves. Microwaves travel at the speed of light. Now, I know that sounds funny. You say, well, why do they travel at the speed of light? We call it the speed of light, but light belongs to an entire spectrum known as electromagnetic waves, and all electromagnetic waves, microwaves, infrared, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, they all travel at a velocity of 3.0 times 10 to the 8 meters per second. Okay, so that's the velocity. Now, I've given you the wavelength, I've given you the velocity, and I'm asking for the frequency. And is there a relationship? There is. So lambda multiplied by the frequency is equal to the velocity. Okay, so there's that equation. This is the sort of most fundamental equation about waves. And the velocity, that never changes. Okay, so for all of these waves, all electromagnetic waves, they always travel at 3 times 10 to the 8 meters per second. Okay, that's like 300,000 kilometers per second. But the lambda changes, and if the lambda changes, the f changes such that lambda times f is always equal to that 3 times 10 to the 8. Okay, so can you have different lambdas? Yes, but given any lambda, there's a corresponding f such that when you multiply the two together, you get 3 times 10 to the 8. Okay, great. Well, I told you lambda was 5 centimeters, but convert that to meters. Okay, so 0.05 meters multiplied by f must equal 3 times 10 to the 8 meters per second. Okay, so everything there now is in MKS. This is in meters. That's in meters per second. So f will come out in per second or hertz. Okay, and so what's that equal to? F is equal to, let me do that on my calculator, divided by 0.05, and that. Okay, that's a big number, and that's in per second or hertz. Okay, let me write per second. Okay, and that's a big number. So there's 3, there's another 3, and there's another 3. Okay, so that's kilo, mega, and when you've got 9 zeros, it's giga. Okay, so that's equal to 6 gigahertz, like that. Okay, so there's your answer. And actually, if you look at the back of the microwave, your microwave, it does have like an FCC rating, and it tells you the frequency, and it should be around 6 to 7 gigahertz. Okay, so there you go. Now, what does that mean? That means that your microwaves actually oscillate at a rate of 6 billion times per second. Okay, so this is very fast, but it's happening at the microscopic level. All right, very easy problem, but there you go, and an example of lambda f is equal to v, or v is equal to lambda f. Okay, the only subtle thing about this is you always have to remember that v doesn't change for a particular wave. Say electromagnetic waves, v does not change. All right, last problem. Let me see if there's any questions in the chat. Nope. Okay, last problem. So this is a standing wave problem. Okay, so whoops, cut off slightly. Okay, there we go. So the linear density of the low E string on a guitar. So if a guitar has 6 strings, the thickest string is low E. Okay, the thin string is high E. Okay, so the thick string has a density, a linear density of 5.28 grams per meter. Okay, that means if you take a meter of this string and you clip it and you weigh it, it would turn out to be 5.28 grams. Okay, and it has a length of 76.2 centimeters. So like how a guitar has like a bridge at one end, like on the body of the guitar, and then at the neck where the keys are, where you can tighten and loosen the strings, there's another bridge. So the distance between those two bridges, that's the length of the string that can actually vibrate. That's 76.2 centimeters. Okay, and I also tell you that the frequency of low E is 82.41 hertz. Okay, what tension is required to get that frequency? So when you're tuning a guitar, you turn that key there and it increases or decreases the tension in the string. You have to get just the amount of force. Tension is a force. You have to get just the right number of newtons in that of tension in order to get that frequency, and I want to know how much that is. Okay, so let's go through it. I'll give you the equations as we go through it. The first thing we'll notice is what did I give you? Well, actually, let's see what I give you and convert to MKS before I jump into the equation. So I tell you that this linear density is 5.28. Linear density is given the symbol of mu. Let me grab a mu here. Okay, and so that's equal to this. Okay, that's not MKS though. That's in grams. To go from grams to kilograms, you have to divide by 1,000. So that's going to be 0.00528 kilograms per meter. Okay, so the decimal was here. Okay, divide by 10, 100, and 1,000, and the decimal winds up there. Okay, so divide by 1,000, you're moving the decimal to the left 1, 2, 3 times. Okay, so great. So there's our mu. Okay, there's our mu. What else do I tell you? I tell you that the amount of string that's actually vibrating, and I use the symbol capital L for that in the lecture, so we'll use the same symbol here, 76.2 centimeters, and so that's going to equal 0.762 meters, like that. Okay, and what else do I tell you? I tell you that the fundamental frequency, because the string can actually vibrate at more than just one frequency, and I'll show you what those are when we're done, but the fundamental frequency is 82.41. Okay, now what? Well, there's a relationship between the fundamental frequency and the velocity of waves in the string. Okay, and it's this relationship right here. The fundamental frequency is equal to the velocity divided by 2L. Okay, so the velocity can be written as 2L times that fundamental frequency, and we have all those numbers. 2, and L is 0.762 meters. Okay, so there's your L, and your frequency is 82.41, like that. And so your velocity is now too many digits there, but that's okay. We'll round off at the end. Okay, is 125.59 blah 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 meters per second. Okay, so even though these are standing waves, because you're holding the string down at both ends, there still is a velocity associated with those waves. Okay, on the string. Okay, and it turns out to be about 125 meters per second. Okay, now that you have that velocity, you go, well, what can I do with that? There is a relationship between the velocity and the linear density and the tension, and it's this here. The velocity is the square root of the tension divided by the linear mass density, like that. Okay, so this is the relationship that determines the velocity of waves in this string. Okay, so given a string, it has a certain linear mass density. In other words, it's so thick. Okay, it's got a certain thickness associated with it, and you apply a certain tension to it, the velocity is fixed no matter what the wavelengths are. Okay, and that's given by this formula right here. Okay, now we want to calculate the tension, and that's inside the square root, so let's square both sides, and that'll just give this. Okay, we want to solve for t, so let's multiply both sides by mu, because we know mu and we know v squared, like that. And so mu, from above here, it was this number here, like that. Okay, and v squared was this number here. Well, v was this number here, and we're going to square it like that. Okay, and what's that equal to? We will find out. All right, and I'll just, there we go. Actually, let me round it off there. There it is. 83.3 newtons. Okay, so 83.3 newtons. If you were actually producing this, and you're going to do a lab where you have a guitar string, and you're actually going to create a tension on it by putting weights on it, 83.3 newtons roughly corresponds to 8 kilograms, okay? Because 8 kilograms weighs 80 newtons, all right? And so there you go. With just like 8 kilograms of weight pulling on this string, you've got enough tension in the string to give you the low E frequency of 82.41 hertz. Okay, so there you go. There's an example of standing waves. Now there's a lot to the question of standing waves, and so here I asked for the tension, but I could have given you the tension and asked for the frequency. I could give you the tension and the frequency and the length and ask you for the linear mass density. In other words, I could just, out of all the possible variables here, I just leave one blank, okay? And the two equations that you really need are this one right here and that one right there. Those are the two, basically. Let me just draw them or cut and paste them down there. These two equations right here are what govern it, okay? And obviously they're related because there's a velocity there and a velocity there, so both of them apply, okay? And just plug in for what you know in MKS, and you'll be able to solve for the one remaining variable. All right. I did say that I was going to mention something about the other frequencies. I kept saying fundamental frequency of F0 here. If this is your fundamental frequency, that's not the only frequency at which the string can vibrate. It can vibrate at this frequency. It can vibrate at this frequency, 2 times that. It can also vibrate at 3 times that. Whoops. 3 times that. Okay. And it can vibrate at 4 times that, 5 times that, 6 times that, and so on. Okay. This is called the fundamental, and these are the harmonics, okay, or the overtones. Okay. So depending on how you pluck the string, and guitarists are pretty good at this. They can either generate the fundamental frequency. That's the easiest one. If you just pluck the string, you're going to get that. But if you pluck the string in a certain way, you'll get the first harmonic predominantly, because there's always a mixture of a little bit of the other ones in there. And I don't know if guitarists can actually produce this one, but they can definitely produce that one. Okay. All right, that's it for this evening. Let's take a look here in the chat. And three of you have survived to the end. But okay, so if there are no questions, then I guess we're done for the evening. All right, let me just ask any questions. If not, we're done for the evening. There's a little bit of a lag, so I'll just wait a second then. If not, I'll. All right. Doesn't seem like there are any questions. Good. Goodbye, everyone.